Okay, welcome everybody. I know people are probably still filtering in, but I want to make sure we allow all the time for all the talks, so I think we should get started. I'm Michael Koblenz. I'm your session chair for today. I'm from UC San Diego. Welcome to our first OOPSLA session on data compression, in which all of our authors compress years of research into a 15-minute talk. Today's topic is program synthesis. Our first paper will be presented by Zhuo. It's called Asparagus, Automated Synthesis of Parametric Gas Upper Bounds for Smart Contracts. I'm really excited about all the talks today. Go ahead.
Okay, thank you. Good morning, everyone. I'm Zhuo. I'm happy to present Asparagus, which is automated synthesis of parametric gas upper bounds for smart contracts. And this is joint work with Soroush, Amir, and Hitarth from the Hong Kong University of Science and Technology. And okay, so what is smart contract and gas? So smart contract is just programs that blockchain that all the full nodes should execute. So since everyone has to execute it, then calling the public function of smart contract is not cheap. You need to pay transaction fee, and this is called gas. And it's proportional to computational resource, which is time and space. So people write smart contract in Solidity source code, like the code over there, and then it's compiled to this virtual machine bytecode, which is just a list of opcode. And for each opcode, there's a gas defined on this operation. So the gas usage is just the total gas usage of all the opcodes that you will execute in the real time. And so why is it challenging to estimate the gas bound? So most importantly, because the smart contract programmers just write in Solidity. It's a friendly language, but the gas is assigned to the EVM bytecode, which is really ugly. And when the code size is huge, you have hundreds of lines of Solidity code, then you will have thousands of lines in bytecode. And it's really impossible for a human to estimate how much transaction fee you need for this transaction. So, since gas fee is just proportional to the computational resource, and then smart contract is a Turing complete language, it has all the challenge of resource analysis of just common program analysis, like conditional branches or loops. And note that the actual gas usage is dynamic depending on the blockchain state when the transaction is actually handled. But we want to have a static bounds, so it to be parameterized by the real-time state. And one more challenge here that for single opcode, we define a gas, and the gas can be non-constant. For example, the SHA-3 is just computing the hash of a string. The gas usage is linear with respect to the length of the string. And this makes things a little bit more complicated. And then it can be piecewise constant, such as storage writes a value x to a storage. And it depending on the old value and the new value, the gas can take these three different values. So we just use the largest gas cost to be sound. And so now we can present the overview of Asparagus. We take Solidity smart contract as input, and since gas is defined on the bytecode, we need something to compile it and extract the control flow graph of the bytecode. And since estimating the gas is only decidable if we restrain ourselves to polynomial systems, so we need to do some overapproximation to transform it to polynomial transition systems, and then we formulate our problem by adding just invariants and ranking functions. And finally, we reduce our constraint system by the three theorems from real algebra geometry to efficiently solve everything. So I'm introduce the blue parts, which are sound and semi-complete. So one of the constraints, suppose we already processed the system into a polynomial transition system, which is a set of locations, a set of variables, and polynomial transition, which means the variable update is polynomial, and the condition is polynomial inequality, and gas usage also polynomial expression. And we define ranking functions, which we call remaining gas polynomials, just ranking functions rated by gas usage. And we also might need inductive loop invariants. And these or polynomials on the program variables v. So this was one example about the ranking function at location L1. So like winning vote count is the program variable, and these t's are the temporary coefficients that we don't know, but we want to solve. So overall, we will formalize the problem as constraints on the program variable v and the template coefficients t. And the constraints just saying that, okay, you have to satisfy the requirement of ranking function, so at each transition you have enough guess, and then also you satisfy the definition of inductive invariance for those template invariants. And so overall, the format of the constraint really looks like this. So exists some value for the template coefficient, and that for every possible value of the program variables, as long as some polynomials on these variables are non-active, then some other polynomial is non-active. And this means the inductive variance hold or ranking function is positive, something like that, and then you have enough guess, and then the variant hold after the transition. So if we can solve this constraint system, that basically means we can get a solution for this t. Then this basically means we have a valid guess upper bound. So now the problem is to solve it. And recall that we have this format of constraints, and our goal is to find a valid solution for template variables t. But the challenge, if we just directly pass it to the estimate solver, is that they have this universal quantifier on the program variable v, and this is really difficult. So the solution is to use these theorems for the quantifier elimination, and this is our main theoretic technique. So we use Farkas Lemma for linear transition system, and then use Handelman and Putinar for the polynomial transition systems. And after this processing, we output a system of quadratic constraints with only the existing show quantifier on the template coefficient. So v doesn't appear here. There's no universal quantifier here. And this system can be efficiently solved by SME2 solvers, so we get the solution. And next, we introduce each of these three theorems. Firstly, using Farkas Lemma, suppose this works for the linear systems. So suppose the constraint is like for all v, then if some polynomial on t and v are non-active, then it implies that g is non-active, and all of these f and g are just linear. Then by Farkas Lemma is saying that this is equivalent to saying that g can be represented as a non-active linear combination of all the f's. So these, at the left-hand side and right-hand side, if you think of them just as polynomials on v, and then two polynomials are equal, only if each pair of corresponding coefficients are equal. So, and the coefficients are just expressed by constant and then template coefficients. There's no v in this coefficient, so we get another constraint system that only has t and some new lambdas, and then some non-active constraint without v. Okay, to see example, suppose we have program variable v's and the template variable t1, t2 that we want to solve, and then we have f1, f2 are polynomials on v, and then g. And our goal is to find t1, t2 such that for all value of v's, if f1 and f2 are non-active, then g is non-active. And by Farkas Lemma, it says g can be represented as linear combination of f1, f2, and coefficient of each term should be the same, and term for the constant is g is like this, and then term for the term v1, for the term v2, for the term v3, the coefficients are like this, and these coefficients should be equal. And then we also have the lambdas should be non-negative. Then this theme is a constraint system with only existential quantifier on the template coefficient. So we can pass this to SDMT solvers, and they give us a solution, and one possible solution is this. And then the value for T1, T2 are what we need. And for polynomial case, we need other theorems. So Handelman basically says that so the constraint form is still similar, and he says that it's equivalent saying that G can be represented as a linear combination of F1, F2, but also contains this F1 squared, F1, F2. So basically, linear combination of all products of powers of Fi. So, and in practice with bounded degree, so it can be represented finitely. And then again, two polynomials over V are equal. We just match the coefficients and get new constraints without program variables, and then we can solve it. I have a simple example here. Like the Handelman's theorem can infer such kind of constraints. Like if V1 is non-active, then V1 squared is also non-active. And can be a more complicated example, like we can have system like the two linear inequalities can imply a quadratic inequality by representing this quadratic inequality as linear combination of F1, F2, and then F1 squared. And the match the coefficient, get a constraint and solve it. And then a stronger version is Putinar's Positivstellensatz. The intuition is that the sum of squares is always non-active. So without any premise, then these expressions are always non-active. So we can use this and say that, okay, G can be represented as sum of squares plus this thing, where Fi's are here, non-active, and then Hi is sum of squares over V, which is automatically non-negative. And this also can be represented by finite template variables. So with this, we can imply something like this from nothing. So summary, we have these theorems, and with these theorems, we can transfer these constraints with this universal quantifier to a new constraint without this V, but at the cost of increasing the number of template coefficients, these lambdas. And then we have experiments showing that, firstly, the toy one, showing that we can solve a nested loop case. This is code for a simple nested loop, and then this is the polynomial transition system. And Asparagus, our tool, can synthesize the exact quadratic gas bound. And we also perform an experiment on large data set. We compare with GASTAP, which is the only work that estimates parametric gas bounds using some recurrence analysis. But it fails on nonlinear polynomial functions. And we also compare with Solidity compiler, which only estimates constant gas bounds. And the dataset we compare is the dataset used in GASTAP. It has 24,000 contrast-dismant functions. And we show that we are really better than all of the other methods. Firstly, we successfully synthesize gas bounds for much more functions. Like we solve 86%, while they only solve around 60%. And our bounds are also consistently tighter. Like we are tighter compared to a GASTAP in more than 97% of the cases. So we are really better in experiment. So there are some failure cases, and the reason is that might be too many variables, too many branches, too many loops. So our estimate to solvers still get stuck. And it's also possible if it's dependent on some untracked information, such as length of nested arrays due to some weird thing in Ethereum. So that's it. In conclusion, we propose Asparagus, a tool to automatically infer parametric GASTAP bounds for smart contracts, and we use algebraic geometry theories for efficient quantified elimination that is not done before, and it's sound assembly complete for polynomial transition systems. And in experiment, we vastly outperform previous tools. So thank you for attention, and I'm happy to answer any question.
Thank you. So we have a microphone here in the middle. If you want to ask a question, if you could please just go to the microphone. That way we can try to do it quickly.
Hey, that was very interesting. Thanks. So I had two questions. The first one's kind of quick. How much overlap was there in the failure cases between GASTAP and the Solidity compiler? Like, did Asparagus fail on a subset of things that GASTAP also failed on, or was there like no overlap? Yeah, sorry. So the cases, like the failed cases, the 13%, like, is that 13% like a strict subset of the, I don't know, like 38% that the Solidity compiler failed on, or is it different?
Yeah, it is almost with maybe 2 or 4 like different that we didn't solve, but they solved. But comparing to these tens of thousands of functions, then it's really negligible, and that's mostly due to the we use some tools to transform the Solidity code to the bytecode, and they might have some more optimization to parse more information than us. So it's not about our theoretical ability.
Cool,
Thank you for the question.
Yeah, sorry, just one more. Did you guys measure the performance of the constraint solving? Like how long it took to just solve the constraints?
So in reality, we just set a timeout. We set timeout for only 10 seconds. And so we compare with GASTAP, it also use 10 seconds timeout, so it's a fair comparison. If we have more time, we might solve more cases.
Okay,
yes.
Thanks.
Thank you.
Hi, thanks for the nice talk. So you said that you work on EVM bytecode, is that right? Like, are you analyzing the bytecode?
Yes, so here we work on bytecode, but more specifically, we need some tool to just tell me that what the variables, like in the bytecode, is just push pop, and we need to analyze like these are the stack variables and corresponding to the program variables in the source code, and we use other people's tool to do this. So finally, we just got our polynomial transition system.
Right. So my question was actually, so sometimes people write these smart contracts with inline assembly, and I was just curious if you have any issues with handling inline assembly, or if you have encountered that.
I don't know. I think in my data set, every code is just source code, and then we use other people's tool to do that, and this is not our main contribution. Our main contribution is how we solve the constraints and how we use these theorems to reduce the constraints.
All right, thanks.
Thank you.
Thank you very much. Let's have one more round of applause for our speaker.